Okay, hello everyone. Welcome back to the Intercontinental Seminar Series of Gravity and Cosmology. So today we are very happy to have Professor Sonny Vagnozzi to be our speaker. So Professor Vagnozzi, he got his PhD in 2019 from Stockholm University in Sweden, and later in 2019, he went to a University of Cambridge to take up the Newton Cavity Fellow as at the Cavity Institute for Cosmology. And in 2022, he went back to Italy as the faculty position in University of Trento. So today he is going to talk about 5 brief lessons on the Hubble tension. Without further ado, the stage is yours, please.
Thank you, Shayu. Thanks for the introduction and also the invitation. So today I'll share 5 short lessons on the Hubble tension. And in case you didn't get this, the title is inspired from Carlo Rovelli's book, 7 Brief Lessons on Physics. Just since this is not a detective novel, I'll give you straight away the lessons and we'll get back to them in due time. First of all, I'll give a brief introduction on what the Hubble tension is for those of you less familiar with the topic. And those of you who are familiar with it will probably have heard the phrase that the Hubble tension requires new physics before recombination. This is correct, but in the first lesson I'll share, I want to convince you that new physics before recombination is not enough on its own. The next logical step is to try and build a model combining new physics before and after recombination. I'll show you with a specific example why this is in fact very difficult. And in doing this, we'll appreciate the key role played by the matter density and the physical dark matter density, omega m and omega c, in the Hubble tension. So the third lesson I'll share is about how the Hubble tension is really a multidimensional problem and why focusing just on the Hubble constant is somewhat misleading. In the fourth lesson, I'll address the question of how local structure can impact measurements of the Hubble constant, and I'll try to convince you that it can actually make the tension even worse. And the final short lesson is about the recent BAO data from the DESI survey and whether or not it changes the overall picture I'll present. The answer is no. And since a lot of this work, in fact, almost all of it, is done in collaboration with my junior collaborators to highlight their contributions. If you see a person's name in blue, that's a student, and in red, it's a postdoc. Okay, so what's the Hubble constant? The Hubble constant is the current rate of expansion of the universe, and it's always been one of the most important numbers in cosmology. Adam Rees in 2019 described the Hubble constant as the ultimate end-to-end test for lambda CDM. What does this mean? It means that we can try to infer it from opposite ends of the universe, in one case in a more direct way when we move from our location outwards, or we can do the opposite, move from outwards to our location, making some assumptions, and if the underlying assumption is correct, then the two measurements should agree. Okay, and this is a end-to-end test which the lambda CDM model seems to be failing. So how do we measure the Hubble constant? In cosmology, it's always a good idea to measure distances, especially if you want to infer the expansion rate. So distances carry an integral dependence on the expansion rate. So you can more or less directly read off an expansion rate when you have measurements of distances as a function of redshift. Now, in cosmology, we can't really measure distances. What we can really do is infer distances from the only, exaggerating a bit, in cosmology, we can only really measure fluxes or angles, okay? But from these two measurements, you can read off distances. And this works if you have classes of objects of which you know either the intrinsic luminosity, in this case, we talk about standard candles, or the intrinsic physical size. In this case, we talk about standard rulers. And rulers and candles play a key role in the Hubble tension. Because if I go back to this picture, when we move out from left to right, we are really using candles. And when we move from right to left, we are really using rulers. and candles and rulers disagree basically on the Hubble constant. So let's look at how we can move from our location to the outside of the universe to measure the Hubble constant. One of the best known ways for doing this is to build what's known as a distance ladder. And the most famous distance ladder uses supernovae. So the end goal is to get to this quadrant here on the upper right. We want to measure essentially the luminosity distances of supernovae against redshift, okay? And from the intercept of this relation, we can basically read off the Hubble constant. Now, the problem is, how do you get the intercept? You need to calibrate this distance redshift relation. And to do so, we move down one rung and we use Cepheids. So Cepheids, thanks to the period luminosity relation, we can determine distances to them. And we can use these distances exploiting galaxies which host both Cepheids and supernovae to calibrate the third rung. But we also need to calibrate the second rung in first place. And to do this, we need anchors which have geometrical distances. If we can find anchors which also host Cepheids, we can calibrate the second rung using geometrical distances. Okay, so this is a 3-rung distance ladder which requires a geometric calibration in the first rung and the Cepheid calibration in the second rung. Now, there are many other distance ladders, but this is simply the best known one. And one of the most recent applications is by the SHOES team, led by Adam Rees. And measurements using this method typically lead to a Hubble constant of about 73 plus or minus 1, give or take. Okay, so we are talking about a percent level measurement of the Hubble constant. There have been improvements after these measurements, but the ballpark value is pretty much stable around 73 or so. Okay, so that's one example of how we can move from our location outwards in the universe. What about, and this method made use of candles, okay, so luminosity distances. Now, how about the opposite direction, moving from the early universe up to today? And this essentially uses rulers. One example of a ruler is the CMB. The CMB, at least within lambda CDM, is a self-calibrated standard ruler. Okay, so simplifying things a lot, in the CMB power spectrum, you see on the left-hand side, there are 3 main classes of features. On very small multiples, so very large scales, you see the imprint of inflation. These are modes which were super-horizon at the time of recombination, so you're really seeing their initial conditions post-processed by some late-time physics. In the intermediate range, you are seeing the imprint of sound waves which froze at recombination. And these sound waves are the ones we use as ruler. And on smaller scales, the spectrum is highly damped because of diffusion of photons at the last scattering surface. Now, the idea is that the sound waves imprint as hot and cold spots in the CMB sky with a typical separation, which is given by the sound horizon. And the angle subtended by this typical separation. Now, it's not an angle which you can directly observe. You can really see it in a statistical sense. But a very sketchy cartoon idea is on the right-hand side here, okay? So we use this measured angle, which is of order 1 degree. And we know what is the physical size of this feature, the sound horizon. And we can therefore infer the distance to the CMB. Now, this angle, theta s, which is the acoustic angular scale, this is the scale subtended, the angular scale subtended by sound waves at recombination. This is of order 1 degree, and it's measured to exquisite accuracy. Now, this angle is very well measured, but both the numerator and denominator are highly model dependent. So let's see how the CMB self-calibrates itself within lambda CDM. Let's look at the numerator first. The numerator is the sound horizon. This is the distance sound waves travel, basically from reheating up to recombination. And it's given by this integral over here, where 3 quantities essentially enter. The first is the physical photon density, which we know extremely well from measurements of the CMB monopole temperature. And we have the sound speed of the photon baryon fluid. We have the physical baryon density, omega b, in red. And this we can infer from the relative height of odd and even peaks to very good precision. And then in green, we have the physical dark matter density, which we can infer from various effects in the CMB. So essentially from the CMB, observing the whole spectrum, we get all the ingredients we need to compute the numerator, at least within lambda CDM. What about the denominator? The denominator depends on three ingredients, okay? We have the red and blue ingredients we already saw before. So the only remaining ingredient is the physical dark energy density, omega lambda, which in some sense is unknown. But now we know the numerator, we know the ratio between numerator and denominator, this angle, which is measured. So we can work out the only free parameter in the denominator, which is this physical dark energy density. And once you know this, at least in lambda CDM, you know the whole evolution of the expansion rate of the universe up to today. And that's how, within lambda CDM, with the CMB, you can self-calibrate this ruler to get the Hubble constant. Okay, so this is really, this cartoon triangle, it is really the physical picture of what's happening. And if you apply this ruler using Planck data alone, you get a value of the Hubble constant in the ballpark of 67 point something. And if you use a totally different experiment, which is ground-based, which is the Atacama Cosmology Telescope, so totally different instrument, totally different systematics, you get a value which is in very good agreement with Planck. So if there is some systematic in the CMB value of the Hubble constant, it has to be very subtle. Now, the CMB alone, in principle, is enough within lambda CDM. But if you go beyond lambda CDM, especially if you imagine new physics after recombination, it's very important to stabilize the CMB constraints using other late-time measurements, basically guardrails. One class of measurements are baryon acoustic oscillations. So this BAO, they basically measure the same feature that sound horizon I showed you before, but not at recombination, but at late times, imprinted in the clustering of galaxies roughly between redshift 0 and 2.5. And what these BAO measurements constrain is the product of sound horizon times Hubble constant. So BAO basically constrain the amplitude of the expansion rate once you calibrate either the sound horizon or the Hubble constant. On the other hand, we also have uncalibrated supernovae, so high redshift supernovae. If we don't calibrate them, what they really constrain is the shape of the expansion rate. So E of z is h of z divided by h naught. Now, these two classes of measurements are in very good agreement with the Planck best fit expansion history in lambda CDM. So in lambda CDM, adding these measurements is more of a consistency check than anything else. But it becomes really important if you go beyond lambda CDM, like if you want to constrain the dark energy equation of state and so on. So if you add these measurements to CMB data from Planck, indeed, you basically confirm the earlier measurement of 67 with a smaller error bar by a factor of almost 2. Okay, so there are many other measurements based on rulers or candles or other probes, which I haven't discussed so far, but they basically confirm the big picture I've shown you. Measurements from the early side of the universe fall in the low range of the Hubble constant, roughly between 67 and 69. Measurements made in the local or late universe tend to fall high instead, closer to 73 or even higher, even up to 75. Okay, so this is a very pictorial representation of the current status of the Hubble constant. Now, where to move from here? The most important insight one can get is to look at the role of BAO measurements. So I mentioned earlier that BAO constrain the product of the Hubble constant on the y-axis and the sound horizon. Okay, indeed, if you take BAO measurements alone plus uncalibrated supernovae, what you get is this green band, which is basically a hyperbola because the product of sound horizon and Hubble constant is a constant. On the other hand, the Planck CMB constraints are this blue band over here, and the local measurement from shoes is this orange band. Now, this plot is very important because it tells you where is the only point in this plot I can get all measurements to agree, and it's where the green and orange band meet, the X over here. So if I want to solve the Hubble tension, I need to move this blue contour over here, which means if I look at the X-axis that I need to lower the sound horizon by about 7%. Again, this is because BAO data gives us the product of the sound horizon and the reduced Hubble constant, which is roughly 100 megaparsec. So this is fit very well if the sound horizon is 147 megaparsec and the Hubble constant is 67. But if you want the Hubble constant to be 73, you need to lower the sound horizon roughly to 136 megaparsec. And what does this tell you? Recall the integral of the sound horizon is an integral basically from reheating to recombination. So if you want to change this integral, you need to change the physics before recombination. And this is why we always hear that the Hubble constant requires new physics before recombination. Okay, and there's no debating this. This is if there are no systematics, there is no doubt we need to fix the physics before recombination. And in fact, one can turn this argument around in many different ways. One can, in fact, take BAO data, calibrate it with local measurements to work out the sound horizon instead of the Hubble constant. And in this case, you find a low sound horizon, which is in tension with any inference of the sound horizon you can get within lambda CDM from early universe measurements, okay? So in this picture, the Hubble constant tension is really a sound horizon tension. So pay attention to this plot. It's going to return later. This is the state of the art in 2019. You know, in this semi-model independent framework, the Hubble tension was at around 3 sigma significance. Or you can turn this argument around further and say, okay, I can combine BAO, which are sparse in redshift, but control the amplitude of the expansion rate at late times, with supernovae, uncalibrated supernovae, which instead constrain the shape of the expansion history. I can try to constrain the late time expansion history and see how much it can deviate from lambda CDM. And the answer, at least in 2016, was not a lot, by less than 10% at redshift below 2. Okay, and this tells you how much room there is for new physics after recombination. And the answer is not a lot, very little, in fact. Okay, so this was all introductory. This was a very quick introduction into the Hubble tension. And now we are ready to dive into my 5 short lessons. The first lesson I want to convey is, okay, we've seen that we need new physics before recombination to solve the Hubble tension. But is this new physics enough? The answer, in my opinion, is no. We'll always need something else. So empirically speaking, over the past, I would say 8 years, there have been many attempts to try and fix the early universe to get a high Hubble constant. And the best attempts only get to a Hubble constant of around 70. So it always falls short of the goal of getting to 73 or so. And this has brought me to think about whether new physics before recombination can be the end of the story. From a more sociological perspective, you know, I've been somewhat worried that the statement, the Hubble tension calls for early time new physics, may have been uncritically interpreted as the Hubble tension calls only for early time new physics. What I want to convince you is that this word here in bold, exclusively, should not be there. So in this paper I've screenshotted here, which I wrote 1 year ago. I worked out 7 different hints which support my statement that new physics before recombination cannot be enough, will never be enough to solve the Hubble tension. As an aside, why exactly 7? There is, well, 7 has many magical properties, but there's a very famous paper in a psychology paper, which is one of the most cited paper in all of academia. by this guy called Miller, which stated that the maximum amount of items an average person can hold in their short-term memory is 7 plus or minus 2. Okay, so 7 is a very good number in this sense. So today I won't discuss all of the 7 hints, but I will discuss 2 of them just to give a flavor. Now, these 7 hints can be divided into 3 classes of hints. In the first class of hints is about the fact that if I just reduce the sound horizon, I am going to introduce other problems elsewhere. The second class of hints is that just as we have guardrails, BAO and supernovae at late times, there are also more subtle guardrails at early times. And within lambda CDM, there is a high level of
Hello, Sunny. It seems that the speaker is problem is the connection.
Chayu, can you hear me
Yes,
again?
yes,
Yeah,
you're
sorry,
back.
my connection was lost. I guess I
Okay.
was here, right? Sorry, I need to share my screen. Yep, I guess I was here, right, when you lost me.
Yes.
Yeah, I was saying that I'm going to now discuss 2 examples of these 7 hints. And they will both fall in class C. So I'll show you that if we try to analyze some late-time datasets in a way which is totally independent of pre-recombination physics, we'll always find that something is missing in lambda CDM at late times. Okay, the first example I want to discuss is about the ages of the oldest astrophysical objects. Now, those of you who are sufficiently old in the audience, so definitely older than me, might remember that historically, the first indications that something like dark energy had to be in place before it was actually discovered came from the fact that astronomers kept observing objects at high redshift, which were apparently older than the universe itself. So back then, the universe did not contain dark energy in the mind of cosmologists. This problem was easily solved by introducing dark energy, simply because if we have a cosmological constant, and therefore the matter density parameter omega m is less than 1, the universe becomes older at any given redshift. Because of course the universe has to be older than any object it contains. That's obvious. So after the discovery of dark energy, all astrophysical objects did not get much attention in cosmology. What I argue is that they can be important again in the context of the Hubble tension. And the reason is the following. Let's go back to one of the most basic formulae in cosmology. This is the age of the universe at any redshift in a FRW cosmology. Now, leaving aside the details of the integral, the important thing is that this integral goes like 1 over the Hubble constant. Now, which means that if I require that the universe has to be at least as old as the oldest objects it contains, I can use this to set an upper limit on the Hubble constant. Because if the Hubble constant is too high, this integral is going to be too low. And it's going to go below the ages of the oldest objects. Why this is interesting in the context of the Hubble tension is that this integral, despite running from z to infinity, it really only cares about late times. It picks up most of its contribution at redshift below 10. So it really doesn't care about what happened at recombination or before, okay? So this upper limit on H naught we can get, if we assume the lambda CDM expansion history in here, it's going to be a very powerful consistency test of lambda CDM. It's going to tell you, is lambda CDM fine at late times, independently of what happened in the early universe? Now, to make this work, you need to find ages of old objects at redshift z greater than 0. And these are very hard to estimate robustly. Most of the ages of astronomical objects we have are at redshift 0, basically. Now, let's say we play this game and we find an upper limit on the Hubble constant, which contradicts local measurements from shoes, for example. Then what we can conclude is that either lambda CDM is broken at late times, z less than 10, because that's the range this integral cares about, or we might need new physics on local scales to fix the shoes measurement. Whichever conclusion you draw, it's going to be completely independent of what happened in the early universe. So with my colleagues in Harvard, Fabio Pacucci and Avi Loeb, in 2022, we started from catalogs with millions of galaxies, especially from the Candle survey, and we extracted those objects which were oldest in any redshift bin. So we came up with this catalog of 114 very old astrophysical objects up to redshift roughly 8. And then we ask ourselves, what do they teach us about the Hubble constant? So this curve in blue is the age-redshift relationship for a universe with a Hubble constant of 70. And you can already see that most of these old objects fall close to this blue curve. So you can expect an upper limit on the Hubble constant of order 70. And if we go and play this game, we find, in fact, an upper limit at 2 sigma of 73.2, which is if you work out the statistics properly, is in roughly 2 sigma tension with the local measurement of the Hubble constant from shoes. Now, if you take this limit seriously, if we trust the ages of these objects, which is a huge caveat, you can get to 3 conclusions. Either lambda CDM is not the end of the story at low redshift, so we need new physics, which makes the universe a bit older at all redshifts. Or maybe lambda CDM is fine, but then you need new physics on local scales to fix the shoes measurement. Or this could just be a 2 sigma fluke, of course. Now, it so happens that if we take the first option seriously, the new physics you need is of the type which makes the universe older. So something like phantom dark energy or similar, something with an equation of state below -1 would indeed help. And that's also the type of new physics which can help raise the Hubble constant. Okay, so the type of new physics at late times you need here is also something which can help with the Hubble tension to some extent. This was the first hint. So as you see, the first hint is about analyzing data in a way which is totally independent of early time physics and finding that something is broken at late times or on local scales. And this something, new ingredients which will fix this would also help with the Hubble tension. The second hint is about something I call descending trends, and it's a bit more mathematical in nature. So whenever I have a dynamical model like lambda CDM, this model, I can say that it breaks down if values of constant fitting parameters are not constant in time. Let's be more specific. If I give you, within an FRW universe, a prescription for the effective equation of state, W effective, I can integrate this to get h of z, the expansion rate, as a function of an integration constant h naught. But I can also turn this equation around. I can move h of z from the left-hand side to the right-hand side and move the integration constant to the left-hand side. And this is still mathematically correct. So what do we have here? We have h of z in blue is basically data. W effective is basically your model. This equation is telling you that model and data, if model and data agree with each other, you can infer a Hubble constant, which is an integration constant and should therefore be a constant in redshift, okay? But if your model and data do not agree, what you're going to see is that on the left-hand side, this Hubble constant is going to run with redshift. It's going to run in such a way to compensate this disagreement between data in blue and model in red. Okay, so how can you apply this in practice? You can apply this by noting that if the Hubble tension is physical, in the sense that it's not due to systematics, but it's really due to new physics, and if there's new physics involved at late times, then lambda CDM is wrong. Therefore, if you put in lambda CDM here in the red part as the model, and you analyze late time data, and you try to infer the Hubble constant in different redshift bins, you should see the Hubble constant evolving in redshift to compensate this mismatch between lambda CDM and data. So the question is, have we observed any redshift evolution of the Hubble constant in late time data? And if we observe some trend, has this trend been consistent across different probes? The answer is yes. And the most famous example is from 2019, and it's in the Holy Cow strong lensing data. So the Holy Cow experiment, they made this plot, which was relegated to an appendix, where they tried to infer the Hubble constant, not from all 6 lenses together, but from each lens individually. So you can clearly see here a 2 sigma trend with the Hubble constant decreasing as a function of lens redshift, which is exactly, this assumes lambda CDM, of course, which is exactly the type of trend I described here, okay, if you have a mismatch between lambda CDM in red and data in blue. And following up on this, there's been a lot of work done by other groups, what has been consistently found is that different late-time data sets analyzed in different ways all show a similar trend, okay, a similar between 2 and up to 3 sigma trend of a Hubble constant decreasing with the Hubble constant decreasing with the redshift bin at which it is inferred. So besides these probes I showed you, there have been many examples in recent years. I just quote some examples here using supernovae data, cosmic chronometers, quasars, and even similar trends have been seen in S8, so the clustering parameter, which instead of decreasing with redshift is actually increasing. Now, the question is, maybe you could in principle expect such a trend even in lambda CDM, because naively you would say that at high redshift, if you go above redshift 2 or so, you lose sensitivity to dark energy. So you might expect omega m to go up and h naught to go down. But analysis on mock data suggests that in any case, the effect which has been seen here, which I've shown you, and in all these other papers, is too big, has a too large significance, and should only be seen at a higher redshift. So if we take all these trends seriously, which are now at almost a 3 sigma level, this means that something is broken in lambda CDM at late times, especially at redshift below 2 or so. And again, if you want to fix this trend, if you want to bring this trend to be flat, as you would expect, mathematically speaking, the type of new physics you need is, again, of the type which makes the universe older at all redshift. So whatever fixes hint number 2 would also fix the earlier hint I presented. And again, something like phantom dark energy would go in the right direction and would also help with the Hubble tension. So I won't discuss all the other 5 hints, but some of them are similar in philosophy and some are completely different. But they all point towards a picture where early time new physics, this guy in yellow, is not enough, can only bring us up to 70, 71 or so. So the conclusion I drew is that if we don't believe there are systematics at play, which is of course a big if, we need either or both new physics at late times, this orange guy, which can only be a subdominant part of the game, but can still give an important contribution, which can help raise the cosmological value of the Hubble constant further up. Or we need new physics on local scales, this guy in green, which pulls the shoes measurement down from 74 or so. And therefore, the first lesson I want to share with you is that I think new physics at early times, this yellow guy, is important, but cannot be the end of the story in the Hubble tension. So the next natural question is, can we try and construct a combination of yellow and orange guy to fix the Hubble constant measure inferred from the early universe? And this is something we did in a recent paper with my collaborators, Yo Toda, who I saw here in the audience, William Jarre from Sheffield, who's a postdoc currently on the job market, and Emre Ozulkar in Istanbul, and Eleonora Di Valentino in Sheffield. So we took a specific combination of early time and late time new physics, tried to put them together, and found that they didn't work. And in doing so, we learned some important lessons, which I'll share now. But before going into the details, let's go back to the sound horizon. Let's think about how can we reduce the sound horizon. This here is the integral determining the sound horizon. And as you can see, you have basically three knobs you can play around if you want to reduce it. You can either raise the denominator, so put in more energy density in a pre-recombination universe. And that's what you do, for example, with models of early dark energy. You can play around with the sound speed of the photon baryon plasma, but this is very difficult. Or you can play around with the redshift of recombination. And that's not as successful, but also fairly interesting. And in fact, if you can make recombination occur a bit earlier, you are reducing the range of this integral, so you are going to reduce the integral itself. One interesting way to do so is to have if you had a higher electron mass at recombination. And the reason is that the binding energy of hydrogen, D, is proportional to the electron mass. And therefore, if the electron was heavier, it becomes recombination occurs earlier because it's energetically more favorable for it to occur earlier. And this makes basically raises the redshift of recombination, so makes this integral go over a smaller range. And this is a model which seems to work. It requires some shifts in the physical baryon and matter density, which you can reabsorb if you have a closed universe with negative spatial curvature. So in summary, a model with a varying electron mass and a non-flat universe can solve the Hubble tension you see at a level of roughly, it reduces it to the level of 2 sigma. And in the Hubble tension Olympics paper from 2022, this was indeed the model which won the gold medal. So it's one of the most successful models at present. And so our very naive idea was, let's try and combine this model with some ingredient at late times. Okay, so the ingredient we took at late times is the so-called lambda SCDM model. So what's this? It's a deformation of lambda CDM, which has a instantaneous anti-de Sitter to de Sitter transition at a redshift of roughly 2. So you have a cosmological constant which instantaneously switches sign. So this is purely phenomenological, but in fact, in this seminar series, there was a talk by Antonio De Felice on how you can get this model out of certain modified gravity theories, of course, not with an instantaneous transition. Now, this model is interesting for many reasons. First of all, in order to keep the acoustic angular scale of the CMB fixed, as you lower the transition redshift, you need a higher Hubble constant, as you can see over here. And if this transition redshift is low enough, but sufficiently high, you can basically fit uncalibrated supernovae data as well as lambda CDM, because at late times, this model is just lambda CDM. It can also fit high redshift BAR measurements better than lambda CDM, because there was, you might have seen it in an earlier plot, there is an anomalous Lyman alpha measurement at redshift 2.5. And more generally, among the models of new physics at late times, this is definitely among the least unsuccessful, okay? So it has many interesting features. So what we thought we could do is, okay, let's combine this varying electron mass with this sign switching cosmological constant and see what happens. If you combine something which works well at early times and at late times, we thought we could go, all the way up to a high Hubble constant. And we failed completely. As you can see, the combined models are the ones in green, and the Hubble constant is pretty low, with larger error bars, but still even lower than lambda CDM. So clearly something wrong was happening. The impression is that each model is undoing the positive work of the other one. And that's exactly the case. The varying electron mass is pulling, you can really see this in the matter density parameter omega m. So if you compare the green and gray curves, you can see that if you have only the green curve, which is the sign switching cosmological constant, this is pulling the matter density in a certain direction. If you introduce the varying electron mass, this is going to pull omega m in the opposite direction. And these different pulls result in the two models basically undoing each other. I won't discuss the physical reason why this happens. It's a bit more technical, but I refer you to our paper. But the net effect is that each model is working against the other. So this particular combination did not work. And it suggests to us that it's actually very difficult to combine new physics before and after recombination to get a high Hubble constant. But one thing we learned is that the matter density, omega m, plays a very important role in the Hubble tension discussion, a role which is more important than previously realized. And this brings me to my third lesson, which is about the key role played by the matter density parameter omega m and the physical dark matter density omega c. And this is work we recently put out on the archive, led by my students Davide Pedrotti and Jinqiang Jiang, and postdocs Luis Escamilla and Simoni Santos. So to see the important role of omega m, let's write out what omega m is. We can write it in terms of the physical baryon density, omega b in green, the physical dark matter density, and the reduced Hubble constant. Okay, now let's assume that omega m is fixed. It's calibrated in some way. And let's assume omega b is also fixed, calibrated. What this means is that for this equation to hold true, if I fix the blue and green ingredients, then the red ones, the physical dark matter density and the Hubble constant, have to move together, have to either increase together or decrease together. That's just a mathematical statement. The question is, are these blue and green measurements fixed? More or less. We can calibrate omega m using BAO and uncalibrated supernovae, and we can calibrate the physical baryon density using BBN, because the physical baryon density has a huge effect on the abundance of light elements. This then means that if we increase the Hubble constant by some fractional amount delta H over H, the physical dark matter density has to increase, it has to have a fractional increase about 2 times as large. Now, in reality, this number 2 is closer to 2.4 because of the effect of massive neutrinos, which I haven't accounted for in here. Now, this has important implications because if the physical dark matter density increases and the physical baryon density is fixed, also the physical total matter density is going to increase, which means that matter radiation equality occurs earlier, matter perturbations have a longer time to grow, and therefore we are going to raise the clustering parameter sigma 8 and also S8. Okay, so if you want to solve the Hubble tension, you must raise S8. So you are going to worsen the tension between CMB and weak lensing measurements. Okay, and again, you can show that the fractional increase in S8 has to be roughly twice the fractional increase in delta in the Hubble constant. So we tested this explicitly on real data. You can see over here what happens if we calibrate late time data using either the low sound horizon from Planck or the high Hubble constant. You can see that the physical matter density does indeed increase with the Hubble constant. And this black line is this 2.38 I showed you before. And you see this increase follows very well the analytical expectations we had, and the same holds for S8. So the conclusion we drew is that omega m and omega c play critical roles in the Hubble constant business, and in particular that anything which fixes H naught, be it at early or late times, must necessarily increase S8 and worsen the tension with cosmic shear measurements. Now, this argument I've just presented you is based on omega m being well calibrated. Is this actually the case? Well, at present, there is some tension at the roughly 1.5-2 sigma level between the value of omega m from different probes. And in particular, different supernovae probes disagree mildly on what omega m is. And I think it is of crucial importance for cosmology to nail down omega m as soon as possible. And this is something which can really help us make progress in the Hubble tension business. Okay, so if cosmologists could ask for a present from Santa Claus, I think it should be, what is the value of omega m chosen by nature? Okay, in a way which is as model independent as possible. Okay, then we move on to my fourth short lesson. So far, we discussed physics in the early universe and in the late universe. But what about local scales? Can they play a role in the Hubble tension? You might remember up to some time ago, there were discussions about voids and how they could alleviate part of the Hubble tension. But let's talk about something we know exists. We know it's there in the local universe, Laniakea. Laniakea is basically it's a supercluster. It's the supercluster where we live in, and it's our home in the cosmos. More precisely, Laniakea is a gravitational basin in the sense that any streamline starting inside Laniakea is going to stay within Laniakea. So you can think of it as a self-gravitating structure, loosely speaking. Now, one natural question is, we have this huge superstructure around us. Is it impacting measurements of the Hubble constant in any way? And that's the question we try to address in this paper led by Leonardo Gianni, who is also on the job market currently with other collaborators at the University of Queensland. And to do so, we proposed a toy model for Laniakea, which is basically an ellipsoidal inhomogeneity with triaxial expansion, so expanding at 3 different rates on the 3 axes. And this is basically inspired by Bianchi type 1 universes, Bianchi type 1 metrics, which are the type of metrics you expect to describe gravitational collapse from inhomogeneities. And we try to fit this ellipsoid to Laniakea, and it gives a very good fit. In fact, it's remarkably good. And the best fit ellipsoid is described by 2 axes which are contracting and the smallest axis which is expanding. Okay, so it means that on average, Laniakea seems to be contracting using data from bulk flow data from cosmic flows. And this tells you that since it's contracting on average, it is on average overdense. So it's the opposite of a void, as you could expect. And then we ask the question, how does this structure affect local measurements of the Hubble constant? Because now what's going to happen is that because of these inhomogeneities, you will have line of sight dependent distances, which need to be corrected. So we took the calibrator sample of the Pantheon Plus supernovae, and we ask ourselves, how much are their distances off if we don't account for Laniakea? And you can see over here the map of distances corrections. You can turn this map into a correction in the local Hubble constant inferred from the SHOES program. And it turns out the Hubble constant should be even larger if you account for Laniakea. So it goes in the wrong direction of fixing the Hubble tension. So it makes it even worse. Why is delta H not positive? The reason is basically that Laniakea is on average overdense. So inside the expansion rate is slower. And so now if I have a source outside Laniakea, for it to have the same apparent magnitude as in our FRW background, we need the expansion rate outside Laniakea to be larger to compensate for this effect, okay? And if you think back to the void analogy, this is really the opposite of a void. So the same way a void can help with the Hubble tension, a structure like Laniakea, which we know exists and we can model it extremely well, actually makes the Hubble tension slightly worse. And the final lesson I want to share is about the recent data from DESI. In April, the DESI experiment released the first set of BAO data, which seemed to be in slight tension with lambda CDM. The question is everything I told you so far, is it affected in any way by the DESI measurements? We addressed this question in a recent paper we put on arXiv, produced within my group and led again by my PhD students, Jinqian and Davide. We took the DESI data at face value and tried to reconstruct the late time expansion history in a way which is as model independent as possible. So we used Gaussian process regression. Here you can see over here the reconstructed expansion rate and distances. The details are not important, but you can see if you compare, for example, DESI in blue with the earlier SDSS BAO measurements, you can see that DESI has some oscillatory features in the expansion rate, but if you compare blue and orange. But let's zoom in more detail in this plot, the unnormalized expansion rate. You might recall I showed you earlier a plot based on the 2016 paper, which reconstructed the late time expansion rate using only BAO and supernovae and found no more than 10% deviations at redshift below 2. This result persists even if we take the puzzling DESI data at face value. You can see that the reconstruction of the late time expansion rate relative to lambda CDM does not allow for more than between 5 and 10% deviations at redshift below 1.5, a bit larger up to redshift 2, but that's mostly due to the absence of a lot of data there. So even with DESI data, the shape of the expansion history is constrained to within 10% to that of lambda CDM. So there is still no room for new physics at late time alone to solve the Hubble tension. This becomes even more evident if you take this plot, which is the 2024 analogous of an earlier 2019 plot I showed you, where we infer the sound horizon from basically from this reconstructed data. For different dataset combinations at current time, in a totally model independent way, the Hubble tension still ranges between 4.7 sigma and 6 sigma, depending on which data you take. So even with DESI, the Hubble tension is pretty much still there. It hasn't gone away. And everything I told you so far is still true. You still need new physics, which is going to lower the sound horizon from the green band down to this blue value. Yeah, sorry, you lost me again, but I'm basically done. Let me just share my screen. Sorry for this. Okay, so I was at this second to last slide. Let me just recap again that DESI data does not change anything I've told you about the Hubble tension. Okay, so I'll just leave you again with my 5 take-home lessons. The first is that new physics before recombination on its own is not enough to solve the Hubble tension. But even if you want to combine new physics at early and late times, it is very difficult to find a working model. And the key role in this game is played by the matter density parameter omega m and the physical dark matter density omega c. Structural and local scales, such as Laniakea, can actually make the tension even worse. And the recent data from DESI does not change anything I've discussed earlier. And in fact, the 6th lesson I would like to emphasize is that omega m is really, really important in this story. And we don't know it as well as I would like. We urgently need a calibration of omega m which is as reliable and model independent as possible. And that should be a priority in the cosmology community moving forward. So that's all I wanted to say, and I'm now happy to take any questions.
Thank you very much, Sunny. So I immediately saw a question in the chat.
Okay, let's see. Just a moment. The direct measurement of H naught contains contribution from gravitational particle production, while H naught in CME measurements is indirect through the number density of baryons. Ignoring the effect of gravitational particle production is the reason for the tension. In other words, the direct and CME measurements are two different things. No contradiction between them. What do you think about this possibility? I to be honest, I don't know about it in detail. It's not obvious to me that the direct measurement contains a contribution from particle production because it's based on the luminosity of supernovae. I don't see how that would impact low redshift measurements so much. The answer is I don't know about this possibility. I can't give a detailed answer. I'm sorry. Gravitational vacuum polarization. No, I don't know how to answer this at present.
Any other questions from the audience? So let me ask one. So when you mention the difficulty of combining pre and post recombination new physics, so you will only mention one possibility. Is it the
Yeah.
general tendency that these two types of methods they are kind of against with each other? Do you expect that?
That's a very, very good question. I expect that in principle one can find a working model, but we highlighted that the key point is you need to look at omega m, what different models do to omega m. So you want to find two models which will pull omega m in the same direction when they want to solve the Hubble tension. I thought about some example. There are some examples which come to my mind. We haven't tried them, but I expect that if one thinks in this direction, one can find a combination which could in principle work. It's just less trivial than expected.
So this tendency is also related to the fact that when one tries to improve the Hubble tension problem, one is actually worsening the S sigma 8 problems, right?
I would say
this
that's a related problem in the sense that here we didn't look at S8, but indeed all this S8 was worsened here when we try to fix the Hubble tension. But I would say that's a separate important problem which one should also keep in mind if you put weak lensing into the picture.
Mhm. Any other questions?
Hello. I want to ask some question.
Yes, please.
Yeah, can you hear me?
Yep. Yeah.
Okay, so just as you said, the local structure maybe was the Hubble tension. I just wondering about how is the work on how for example, let's say the local void. Such a local void can somehow help solve the sigma 8 tension. So in your scenario about this non-nuclear model, can it also forbidden such a scenario?
Okay. The only possibility for a local void I know is if you have a very large void. I think I don't remember how many gigaparsec, but it has to be very large because small voids are excluded by the
Yeah,
Pantheon data. Yeah,
yeah,
I think this has
somehow,
been done by people in Hong Kong have looked at this scenario.
yeah.
Maybe it was you, yes. That
Yeah.
I think is still working. I don't know how it fares against the latest data. What was your question about Laniakea?
Yeah, I mean, just as you said, non-kill can forbid forbidden the possibility to solve the Hubble tension. But how about the sigma A tension, the matter
Okay.
density inside the local void?
Yeah. Let's see. We haven't looked at S8 actually. It's much less obvious because I wouldn't know how to model the impact of Laniakea on cosmic shear. Because in the case of shoes, it was easy because we know where each supernova is on the sky, and we can tell exactly basically what's the direction of photons from the supernova going inside Laniakea, so we can correct their distances. For cosmic shear, I think it's much more difficult because you have collective light rays from many sources, and you have to model in a statistical sense the impact of Laniakea on cosmic shear. So it's not obvious to me if
I see.
Laniakea has an impact on S8, and if so, in what direction it goes. Yeah, it's not obvious, I think.
I see. I see. Thank you. Mm.
Other questions? So Sunny, you mentioned that you some improvement on the measurements of omega m is required in order to improve, I mean,
Yeah.
improve the tension. And have you ever estimated like how much more accurate is required in order to have some, I mean, the number
Yeah.
in the improvement?
Yeah, good point. So I think we don't need so much an improvement in the error bar. So the error bar is fine at the moment, but I would like to see all these curves agreeing,
Ah,
moving towards each other. That's what really bothers me at the moment because you can see a almost 2 sigma tension between different measurements. And so I think the uncertainty is fine, more or less, but we need to agree on the central value. But another thing which is important is all these measurements, all these inferences assume lambda CDM. But I would
yes.
like to know what value of omega m nature has chosen independently of any model. And that is something which is very difficult to address because almost anything which can probe omega m depends on cosmology. So you need to assume some cosmology. There are some probes which do not assume a cosmology. One of these is this F-gas. It's a measurement of the gas fraction in clusters. Okay, this is a difficult measurement because there are many astrophysical assumptions. You need to assume GR, but you don't need to assume a cosmology. The problem is that this measurement, as I say, it has many systematics, and the uncertainty is quite big. It's much bigger than this one.
Mhm.
Another possibility, which has been discussed recently, is it sounds crazy, but it's cosmology with one galaxy. It's that if you had one galaxy or even more galaxies, of which you can measure their properties, their astrophysical properties really well, there are very tight correlations between galaxy properties and cosmological parameters, especially omega m. This has been discovered using machine learning methods on the Camel's galaxy sample. So in principle, if we had even just one galaxy, whose properties like I think even metallicity and so on, we can measure super well, we could in principle determine omega m without need to assume any cosmology. Do I trust this? Maybe. It's more like I hope this could be trustworthy. But if it worked, it would be amazing.
Mm.
And this is something which would be perfect because it would give you omega m to a high precision without assuming any cosmology. So I very much hope it would work. I don't really believe it I don't believe it yet. Let's put it this way.
I see. Thank you. And there's another question by Jenny in the chat. So do you really
Yeah.
believe the trend in rounding edge null from strong lensing, given the strong degeneracies in the lens modelings? And which
Okay,
is the
thanks.
which is the most significant and trustful rounding edge null in the late universe? There are two
Yeah, it's a
questions.
very good question, Jenny. I don't believe this trend because as far as I know, in this paper which I reported, there was no accounting for the mass sheet degeneracy yet, and that's one of the biggest contributors to changing H naught. So in a later 2020 paper of the Holical collaboration, they show that if you marginalize over the mass distribution of lenses, H naught goes down and the error bar is blown up by a factor of 3, I think. So yeah, I don't really believe this. This is more like the first hint in this direction. I do believe hints of this trend, which rely on BAO data, supernovae, and I would say also cosmic chronometers. Anything which involves this, I can believe. I can believe, say, to 2 or 3 sigma. Yeah, I would trust them. And this, as you can see, has been seen in many of these probes. So I think there's no questioning the trend is there. People are somewhat debating, I would say, the significance or what it really means for lambda CDM. I hope that answers your question.
Okay, so any other questions? So if there's no question, let's thank Sunny again. Thank you very much for the talk.
Thank you. Thank
And
you again, Chaeyu, for the invitation.
let me stop recording.